We've been talking through the intuition behind tree learning algorithms, and hopefully you've guessed that we can end up in situations where our trees overfit our training data. And so this is an issue that's really important for us to be addressing. In the models that we talked about before we started working with decision trees, each of those models had a fixed number of parameters. So if I had a linear decision surface, I had a coefficient for every feature plus the bias, and that number didn't change as we added, say, more training data. We've also been doing some experiments where we've looked at how well different models perform with different amounts of training data. And we've seen situations where models are very sensitive to the amount of training data, but typically as that training data increases more and more, ultimately our performance tends to plateau. There's also been an implication in there, though we haven't really explored it formally, that as we build more and more complex models with more parameters, we actually need to have more data in order to really nail down our parameter values. And if we don't do that, we risk overfitting the training data. With decision trees, we also have a set of parameters. So in particular, for every question that we've introduced, we have a feature that we have to select as well as a threshold. And then for every leaf node, we have a set of parameters. And if it's a probability tree, then we have that probability function that we're trying to represent. And what this means is that as our tree grows through the learning algorithm, the number of parameters actually increases. So we're no longer in a situation where the number of parameters is fixed during the learning process. And the tree can actually grow, if we allow it, beyond a structure that's really supported by the training data that we have available to us. A very extreme end of this is a situation where we let the learning algorithm execute until every one of our leaf nodes has zero entropy. And even the very far end of the situation is one where we have one leaf node for every training set sample. And in this situation, we essentially have encoded within our tree a custom rule for every training sample. With trees that are sitting on this very extreme end, these tend to be very brittle. And this comes from the fact that the regions that that our tree has learned do not necessarily generalize very well to nearby independent samples. So with tree learning, we have to address this overfitting issue. The general idea is to put constraints on the complexities of the trees that we're learning, and hence we're placing a limit on the number of parameters that we're going to learn. And the question is, what's the best way to go about doing this? Different algorithms, different implementations of algorithms make different choices. We'll talk about a few here. You'll see them in the implementations of individual trees, and then we'll revisit these as we get into situations where we have not one tree but sets of trees. So one simple idea for limiting the complexity of a tree is just to put a cap on the maximum depth that the tree is allowed to grow to. What we mean by this is that going from the root node down to a leaf, we are only going to allow up to a fixed number of questions. And if we have enough training data, what this type of a limit tends to do is it tends to fill out the tree as far as it can grow, and then it stops growing. So we end up with a very balanced kind of a tree. Another approach is to just simply limit the number of leaf nodes that we allow the tree to use. And what this allows the learning algorithm to do is to apportion to very, say, complex parts of the feature space. It allows the learning algorithm to add lots of questions and lots of leaf nodes. And in places where we don't have a lot of complexity, say the class is the same in a very wide swath of the feature space, then the tree learning algorithm can allocate a very small number of questions and leaf nodes. So we're still limiting the overall size of the tree, but we can end up with unbalanced trees, and in lots of situations, this might actually be more appropriate for capturing very inhomogeneous kinds of feature spaces. There are also a variety of approaches where we use the samples that have fallen down into a leaf node to make a decision about whether or not to split that leaf into another question and further leaf nodes. So, for example, we might require that before a leaf node can be considered for splitting, it has to have some minimum number of samples at that leaf node. And if we have only a couple of samples, then it really doesn't make sense to continue to produce splits in order to differentiate, say, one sample from another sample. We can also require a split to make some measurable improvement in the performance of the tree. So in the classification world, we've already talked about change of entropy or the Gini score. These are measures that allow us to talk about how much better a tree is when we add one more specific question and the associated leaf nodes. There are also a variety of statistical approaches to addressing this question, and one is the likelihood ratio test. So the question there is, does the likelihood measure improve as we add that extra structure to the tree? If we're dealing in the crisp classification world, so where the leaf nodes have just one class that they're emitting, then one can actually use something called a chi-squared test in order to measure how much improvement we're getting out of adding that structure. And in both of these cases, the likelihood ratio test and the chi-squared test, we can also ask very careful questions about how much do things improve versus how many more parameters are we adding to our model. And at some point, we just might have added so many parameters that even measurable improvements in performance might not actually be worth it. All right, so that's a few ideas for how we address regularization in trees. You'll see a few of those coming up here in the next video, and then you'll see some of the others as we work through some other ideas in decision trees.